1. AP. Could Mars be a digital simulation humanity has not yet learned to unlock? Could the red plains, the buried valleys, and the pale polar caps be not merely landscapes of rock and dust, but a layer of code, a suspended epic within a larger, unseen system, patiently waiting for a key, a trigger, or a new level of scrutiny to render itself fully? This is not the breathless premise of a space opera thriller. It is a quiet, strange question that rests at the intersection of two uneasy ideas, that reality might be constructed, and that deep time is an eraser of traces. When the question is spoken aloud in scientific cafes, late-night forums, or the muted corridors of research labs, it carries two tones at once. One is the tone of wonder, the honest, almost childlike curiosity that pulls at the seams of the known world. The other is the tone of dread and humility, the recognition that human perception is finite, fragile, and conditioned by a specific scale of time and resolution. The tone shifts depending on who listens. Engineers think of thresholds and protocols. Philosophers think of ontology and meaning. The general public thinks of aliens or conspiracies. But at its core, the question is elegant and simple. What would it mean if Mars were, in some respect, incomplete or archived? To imagine Mars as a digital simulation is to translate geological processes into computational metaphors without abandoning the material facts. A simulation need not be an artifice of malevolent designers. It could be a model, a sandbox, a preserved dataset, or an experiment frozen between iterations. In computational terms, the system running Mars could page out portions of the environment that are not observed or interacted with by agents deemed significant, conserving resources. Features that are not frequently sampled might be stored at lower fidelity. Subroutines containing complex structures, cities, machines, ecosystems might be compacted, archived, or encrypted. The planet might therefore appear barren until some particular kind of probe activates the correct. This metaphor, while speculative, is useful because it reframes the problem of vanished evidence. Archaeology on Earth already wrestles with absence. What is not preserved can be more telling than what is. If Mars once harbored complexity that no longer visibly exists, there are two broad classes of explanations. One is natural: wind, radiation, chemical alteration, and tectonic processes slowly erased the signatures of whatever once stood. The other is informational. The signatures are present but latent, encoded in a medium or at a scale that current instruments cannot yet decode. Both possibilities demand different approaches. The first asks for deeper digging, for better preservation models and more sensitive instruments. The second asks for new ways of asking, for algorithms that the human mind reaches for analogies to make sense of this. It pictures a photograph faded in a sunlit attic, an old operating system image, corrupted and fragmentary, an archive whose index has been lost. It pictures, too, the more human story, a civilization that rose, built, and then departed, taking with it whatever was portable. Knowledge, artifacts, the living, leaving behind ruins that the slow mechanics of the cosmos would confuse for natural formations. This is a story that fits a psychological pattern familiar to humanity: the rise and fall, the elegy for the lost. It is also a story constrained by scale. Even on Earth, the archaeological record is notoriously incomplete. Cities grow and collapse, coastlines change, entire settlement patterns are swallowed by later development or sea level rise. Structures. What, then, would constitute a trace worth chasing? On Earth, stone walls and pottery sherds survive thousands of years, while wooden structures rarely last beyond a few centuries unless in deserts, peat bogs, or arid caves. On Mars, the balance tips further against survival. Organic molecules degrade under cosmic rays, delicate artifacts are ground down by aeolian abrasion, and once liquid water can dissolve, redistribute, or mineralize remains in unexpected ways. Yet some types of evidence could be more durable. Subsurface voids resistant to erosion, dense mineralogical anomalies, isotopic signatures indicating biological processing or industrial activity, and geometric regularities that resist random explanation. To picture an ancient Martian civilization that left after the era ended is to ask how departures happen on planetary scales. Exodus, in this context, might be literal or metaphorical. Literally, a species might leave its home by flight, migration, or evacuation, carrying technology and memory with it. Metaphorically, the leaving might be a transition from active presence to dormancy. Cities could be sealed, active machinery could be shut down, biological communities could be cryopreserved or locked within engineered caches. Why would a civilization choose dormancy over destruction, preservation for future return, avoidance of existential threats, or a shift to a substrate that external observers cannot easily detect? A civilization might have retreated underground. The image of a civilization folding itself away into inaccessible states is hard to hold without sound. It absents the drama of burning cities and the poignant artifacts of a burned bread oven or a child's toy. Instead, it delivers a quieter, more disquieting image, a city that becomes noise level with background geology, a record compressed into patterns indistinguishable from random rock unless one knows the keys. This latter image also resonates with how human memory works. Whole chapters of experience can be archived in ways that are difficult to access later, retrievable only by specific cues. If Mars held a culture that archived itself against cosmic time, the challenge is both archaeological and computational. Modern naturally for testing both the natural erosion and the simulation archival hypotheses, albeit indirectly. Orbiters map mineralogy with spectrometers, ground-penetrating radar reveals buried strata, landers mill and analyze rocks, and rovers roam in slow, deliberate progress, scratching into pale regolith and sending back streams of compressed telemetry. Each instrument operates under its own constraints, its own resolution limits. The activity of a rover is a small, controlled series of interactions. A laser pulse vaporizes a speck of rock. An X-ray spectrometer diffracts photons. A drill shaves off a centimeter of history and exposes fresh surfaces. These acts are precise and intimate. They are, in a way, the means by which humanity nudges at the boundary between the rendered. The psychological landscape here is as important as the physical. Humans bring to this endeavor a constellation of hopes and fears. There is a hope for companionship across cosmic loneliness. The dream that Mars once hosted life, social or otherwise, that could answer questions humanity has not yet known how to ask. There is also fear that uncovering certain truths might upend narratives about origin and destiny, or that evidence of an advanced, vanished civilization would suggest fragile thresholds of survival. On a more existential level, the idea that Mars could be an incomplete simulation raises questions about what meaning humans ascribe to discovery. Would finding an intentionally suspended epoch reduce the wonder of first? The deeply speculative nature of these questions is not a weakness, it is a feature. Speculation operates like an intellectual lantern, illuminating paths that strict empiricism has yet to walk. It encourages the design of new experiments, the development of novel analytic techniques, and the broadening of interpretive frameworks. For example, if researchers entertain the possibility of archived structures, they might develop algorithms to detect anomalous compressibility in radar returns or search for non-natural statistical patterns in the spatial distribution of certain minerals. They might refine models of erosion resilience to prioritize targets for drilling. In other words, the hypothetical becomes pragmatic. It reshapes how one looks. Yet there is a discipline to such looking. Speculation must remain tethered to evidence and to plausible mechanisms. A simulation hypothesis must reckon with thermodynamics, information theory, and the practicalities of computation on planetary scales. An exodus hypothesis must propose energy budgets, transport mechanisms, and timelines that fit within known physics or at least coherent extensions thereof. Without these anchors, imagination drifts into entertainment rather than inquiry. A human mind that contemplates Mars over deep time confronts an overwhelming scale. 10 million years is a thin heartbeat to geology. A billion years is an unfathomable stretch in the domain of human attention. Within such timeframes, whole planetary climates can shift, atmospheric pressure can fall, and oceans can dry. In those epochs, structures either fossilize in immutable minerals, are buried to the point of invisibility, or are reworked into new strata. The sedimentary record is both a palimpsest and an obliterator. For any civilization to persist visibly across hundreds of millions of years would be rare indeed. This framing makes the possibility of detected ruins improbable in the classical sense of standing buildings, but it does not render the search hopeless. The image of an unlocked simulation, however, offers a counterintuitive hope that the universe might retain records in ways gentle to decay and robust to time. If reality uses information compression strategies, some signatures could survive because they are encoded in redundancy across physical patterns. The task for humanity, then, becomes one of decoding, developing the tools to discern crafted redundancy from natural regularity. That is as much a computational problem as it is an archaeological one. In the end, the opening question: could Mars be a digital simulation humanity has not yet unlocked? Did an ancient civilization once live here and then leave when its era ended? Functions as a prism. It refracts current scientific practices into new hues and casts long shadows into theological and philosophical territories. It forces humility about the limits of observation, about the assumptions that guide what instruments are built and sent, and about the narratives humanity constructs when faced with the unknown. It also offers an invigorating promise that Mars, whether archive, simulation, or deeply weathered real world, remains one of the most profound laboratories. This is the premise. It is both a question to be answered and a method to be tried. As instruments sharpen and as analytic sophistication grows, the boundary between what is rendered and what is archived, between what is erased and what endures, will become clearer. In the meantime, the image of a planet that might be waiting, patient as a museum, quiet as a tomb, coded like an unread book, lingers. It invites a careful, reverent approach to exploration, an approach that blends the rigor of science with the humility of a species aware of its own ephemerality and eager, nonetheless, to read what the deep past might still have to teach. What does it mean for a world to be too perfectly dead? The question arrives like a small, stubborn stone thrown into a vast, black pond of cosmic time. Its ripples are not loud, they are thought forms that order the uneasy space between observation and meaning. Mars, from a distance, has always presented itself as an elegant corpse, red dust smoothing into plains, gullies carved and fossilized into silence, polar caps that glint like something neatly put away. There is no rustle of leaves, no chorus of waves, no insect hum to betray processes beneath the surface. The planet's perfection of quiet presses against the human imagination in a way that feels almost too intentional, as if the universe had tidied up when the job was done. To call Mars dead is to say that certain classes of activity, metabolism, reproduction, culture, do not currently animate its surface. But within that shorthand lies an implied texture, a degree of absence. Is the silence coarse and uneven, like a ruined city where wind still moves through broken windows? Or is it exact and clinical, a silence without dust motes, a place where every potential noise has been exhausted and then somehow reversed? Observers notice a subtle difference. Mars does not merely lack life, it lacks the chaotic afterlife of life, the random tumble of detritus, the scatter of artifacts, the noisy residue of biological communities. It is not merely empty, it seems preserved in a state of cessation. There are two images that dominate how this observation is felt. One is geological and cumulative, that Mars exhausted the necessary conditions for life, and, over eons, radiation and wind and chemistry erased much of what might have signaled past complexity. In that image, silence is sedimentary, the product of entropy persistently wearing away at form. The other image is metaphysical and procedural, Mars as a program that has been logged out. This second image is not merely poetic, it is a thought experiment with teeth. It forces consideration of information, residence, and thresholds of interaction. If parts of a planetary system can be rendered dormant, archived, compacted, or suppressed, then the metaphor of a logged-out world reframes decay as a change of representation. In computational systems, large data structures are often trimmed, compressed, or paged out to secondary storage when not in active use. On a planetary scale, the idea translates into the possibility that complex structures could be represented differently in the substrate of matter, encoded into mineral fabrics, distributed as patterns of isotopic variance, or interleaved within stratigraphic noise as low-entropy signals. Such encodings would not look like ruins in the familiar sense. They would be ruins in the code. Subtle statistical deviations, regularities that a geological model would typically ascribe to chance, but that on closer inspection resist that narrative. The human mind is predisposed to see pattern where none exists and to seek agency behind anomalies. This predisposition both helps and hinders. It drives imagination toward hypotheses that can be tested, but it also risks mistaking coincidence for design. The discipline of science is, in part, the creation of methods that can discriminate. On Mars, this discrimination moves in two directions at once, toward the extreme sensitivity of instruments that can detect minute chemical signatures, and toward the development of analytic frameworks that can say, with statistical rigor, whether a pattern stands outside the envelope of natural variability. What would a ruin in the code look like? It would not be a temple standing on a hill. It would be a repeated motif in spectral reflectance that persists across disparate mineral contexts, as if the same information had been inscribed in different media. It might be an arrangement of subsurface voids at scales inconsistent with known impact or sedimentary processes. It could be isotopic ratios in rocks that cluster into discrete bands, bands that imply compartmentalized chemical cycling rather than the smooth gradient expected from diffusion. It might be fractal regularities in surface textures that carry a signature of algorithmic generation, patterns that ordinary geology cannot easily produce without an improbable confluence of forces. Detecting such features requires thinking about ruins the way a computer scientist thinks about corrupted files, look for non-randomness, for compression artifacts, for unexpected redundancy. On Earth, archaeologists recognize the telltale signs of human agency in abrupt regularity. The right angles of a wall, the repetition of identical pottery forms, the ordering of stones into circles. In an informational archaeology of Mars, the equivalents are computational. Low Kolmogorov complexity, where one expects high, statistically improbable sequences, spatial distributions that maximize information content in ways that natural thermodynamic processes rarely do. The instruments humanity currently sends to Mars are blunt, curious hands at the edge of this problem. Spectrometers read color and composition. Ground-penetrating radar sketches the subsurface like a faint thermal imaging of memory. Cameras map patterns with a patient insistence. Each dataset is a palimpsest. Written upon it are both the signals of past processes and the noise of measurement, transmission, and interpretation. The difficulty of untangling these strands is not merely technical, it is epistemological. How does one prove that a deviation is intentionally informative rather than an unusual but natural consequence of physics? The burden of proof is high, because extraordinary claims about intent or design in planetary records. Yet the possibility is not metaphysical fantasy. On Earth, human artifacts have been found where no one expected them. Buried ceremonial sites revealed by regular crop growth. Ancient footpaths shown by subtle topographic relief. Isotopic anomalies signaling managed landscapes. These analogies are instructive because they reveal a principle. Information can survive through forms that are not obvious. On Mars, the survival pathways differ in their chemistry and timescale, but the principle remains. Durable signatures might hide in mineralogical microstructures, in the way magnetite grains align, in subtle variations in sulfur isotopes, or in kilometer-scale regularity that resists the stochasticity of cratering and erosion. To entertain Mars as a logged-out entity also forces re-examination of motive and mechanism, not as moralistic questions, but as physical constraints. If a civilization shows dormancy as a strategy, what processes could convert active systems into low-visibility states that persist across geologic epochs? Burial is one. Complex structures interred under meters of regolith could be shielded from surface scouring. Chemical transformation is another. Organic rich materials could be mineralized into forms that resist detection by traditional biosignature searches. Information migration, a more speculative but physically grounded idea, describes the relocation of functional patterns into substrates that appear inert. The notion that ruins could be encoded algorithmically raises a further conceptual challenge. If information persists, how is it read? Information theory suggests that the interface matters. A dataset archived in a way optimized for a particular class of queries will be invisible to others. A compressed file is meaningless until decompressed with the right key or algorithm. On a planetary scale, the key could be a sequence of observations, a particular sampling strategy, or even a technological capability not yet mastered. This is a disquieting prospect, a planet that yields only the slices of history an observer knows how to cut. It emphasizes that exploration is as much about asking new questions as it is about pointing new instruments. This is where speculation becomes generative. If scientists allow for the possibility of encoded ruins, they can design search strategies explicitly aimed at finding them. Algorithms can be trained to detect anomalous compressibility in radar echoes. Pattern recognition systems can flag spectral distributions that contain non-trivial redundancies. Statistical models can test for modularity in surface features. These approaches transform an abstract worry into a suite of operational tools. The result is not a guarantee of discovery, but a widening of the aperture through which discovery becomes possible. The emotional landscape that accompanies these intellectual moves is worth attending to. There is wonder, which feels like sunlight on a cold morning, the small electric excitement that comes with confronting a universe that possibly contains architectures beyond immediate comprehension. There is also a strain of melancholy, a recognition of prehistorical depths that dwarf human time. To confront ruins, in code, is to reckon with the fragility of presence and the perseverance of information. If some features of the past can be sequestered into formats awaiting competent readers, then much of what matters about civilizations may be what they chose to leave encoded and where. There is also humility embedded in the idea of a planet logged out. It implies that human epistemic reach is partial, that instruments embody assumptions about what is worth sampling and what counts as signal. It invites a more careful stewardship of curiosity to ask not only, what do I see, but what have I not yet taught myself to see? In that way, the logged-out metaphor is ethical as well as scientific. It asks explorers to be patient, to widen their methodologies, and to accept that discovery may be slow and piecemeal. Finally, imagining ruins in the code folds back onto the larger question of meaning. If a world can be archived, compressed, or paused, what does that imply about permanence and legacy? For civilizations on any world, the desire to preserve, to make something persist past the dissolution of ordinary environments, is profound. Humans already undertake their own forms of planetary archiving, from seed banks to digital repositories. Thinking of Mars as an archive forces a recognition that preservation strategies differ from habitation strategies. The archaeological imagination, turned toward information as well as stone, opens new possibilities for what legacy could look like across. Here, then, is the paradox that frames the work of searching. Silence can be a sign of absence, or a refined form of presence. A perfectly dead planet may be a place where complexity once was and has been erased by slow processes, leaving only the faintest of fossils. Or it may be a site where complexity persists in forms that require the right questions and tools to resolve. Both options demand humility and patience from an observing species whose own history is brief compared to the timescales at play. In either case, the planet refuses impatience. It asks that inquiry be careful, that hypotheses be precise, and that the interpretive frameworks include the possibility that information survives in ways subtle and strange. To listen to Mars, then, is to attune oneself to quiet regularities, the tiny deviations from expected noise, the surprising redundancies, the ordered anomalies. It is to accept that the most compelling ruins might not reveal themselves as monuments rising above the dust, but as whispers embedded in the sediment of data. The task of modern planetary science becomes partly a task of translation, learning the grammar of a different archive so that the fossils of processes, the traces of practice, and perhaps even the signatures of intent can be read. Whether Mars proves to be a planet erased by time or carefully logged out by some procedure of preservation, the act of listening will change how humans conceive preservation, time, and the very possibility of finding company. What does it mean when the raw numbers returned from a probe refuse to behave like weathered rock and instead arrange themselves like a poor imitation of manufactured intent? That question arrived in mission logs as an irritant, a phrase in a footnote, an oddly colored thumbnail, a histogram that would not fit the model. It spread through labs not as panic, but as an ache of curiosity, the slow, persistent tug that sits behind every serious scientific anomaly. Telemetry had begun to insist, in its blunt machine way, that some patches of surface were simply too tidy. From orbit and from the ground, instruments told nearly the same story. High-resolution imaging revealed planes of polygons whose symmetry extended far beyond what freeze-thaw polygons typically achieve. Synthetic aperture radar cut through layers and showed subsurface voids arranged in quasi-regular lattices. LiDAR altimetry traced terraces that stepped with uncanny regularity, like levels in a deliberately designed environment. Thermal maps, taken at different times of day, exposed repeating seams where heat dissipated in parallel bands, as if the surface had a modular anatomy. And in every dataset, a slender, persistent feature reappeared, a crack pattern so consistent across scales and materials that it bore the unnatural signature of repetition, the hallmark of a procedural generator, or, to put it bluntly, a glitch. The glitch analogy was unavoidable, and it carried with it a strange blend of amusement and unease. On one hand, the comparison was technical and useful. In digital graphics, when a texture is tiled without care, seam lines become visible. When a level of detail system transitions poorly, chunks pop or stitch in ways that betray the underlying grid. Those are human design errors, neat and repeatable. On the other hand, the analogy suggested a metaphysical possibility that stirred older, more cautionary muscles in the scientific mind. Could the planet be, in part, a rendered surface, a palimpsest of signal and absent routine? The response to that possibility was not uniform. For most observers, the first working hypothesis remained boringly natural. Geology makes patterns. Stress fields, mineralogies, ancient climate oscillations produce ordered forms. Columnar jointing, polygonal cracking in permafrost, rhythmic bedding, and diagenetic segregation can create striking regularities. A mature scientific instinct is conservative. Before imagining the extraordinary, exhaust every terrestrial mechanism. Teams modeled freeze-thaw cycles at scales much larger than ever observed. They generated simulations of desiccation cracks in saline substrates under varying gravity and atmospheric density. They explored the physics of thermal contraction under a thin atmosphere. Each model created that mismatch pushed researchers toward more nuanced statistical tools. Instead of asking whether a pattern could be produced naturally, they began to ask how unlikely such patterning would be under the null hypothesis of geological randomness. They borrowed measures from information theory, entropy profiles, compression ratios, measures of Kolmogorov complexity, and applied them to radar echoes and reflectance spectra. Where natural terrains tended to produce high entropy within certain bounds, some of the suspect regions consistently registered lower than expected complexity, suggesting redundancy. In plain terms, those features carried less information than noise would predict. Repetition suggested a generating rule. The generating rule hypothesis itself split into two directions. One, strictly material, proposed that ancient engineering might have left behind structures that time had not entirely erased, kilometer-scale foundations, regular trenching, or buried lattices of denser rock whose erosion patterns remained stubbornly regular. The other was informatic, that the planet itself, or aspects of it, might have been archived, compressed, or paged out by processes resembling computation. The second idea sounded almost heretical, but it had operational consequences worth considering. If something essential had been compacted into lower resolution representations, then different observational strategies might coax more detail from the same ground. The informatic perspective reframed cracks as seams between data chunks. It imagined a world whose surface held traces of chunking algorithms, boundaries where one representation ended and another began. Those seams could be visible when a chunk's fidelity met the neighbors in conflicting ways. In remote sensing terms, that would look like sudden changes in reflectance behavior, abrupt discontinuities in subsurface radar returns, and repeating lines of structural weakness where the physical medium responded differently to stress. The psychological effect of this reframing was profound. It turned rocks into files and valleys into memory banks. It was a metaphor, certainly, but one with practical teeth. If telemetry recorded boundaries consistent with chunking strategies, then cross-referencing. The debate moved slowly, methodically, as science insists it must. Teams that worked on imaging compared pixel scale anisotropies across wavelengths and sensor types. Radar scientists examined phase coherence across suspected seams. Seismic technicians listened for echoes that would suggest discrete voids or repetitive layering. Where possible, orbital assets were repeated passes, adjusting incidence angles and polarization states, trying to disentangle instrument artifacts from planetary reality. Each new dataset sharpened certain features and blurred others. Sometimes an apparent seam would vanish under a different illumination angle. Sometimes it would resolve into a more complex set of ridges. The planet answered indirectly, like an old recorder playing at a different speed. It was not only the data that changed, the manner of listening evolved. Where earlier missions had prioritized single-point analyses, researchers began deploying systemic tests designed to differentiate between natural regularity and engineered redundancy. Autocorrelation analyses measured how patterns repeated across space. Permutation entropy analyzed sequences of radar returns for non-random structure. Fractal dimension calculations checked whether the geometry of suspect areas deviated from the statistical character of known geological processes. In some areas, the results leaned strongly away from natural expectations, nudging the community into a more speculative posture. Speculation, when disciplined, becomes a creative instrument. It suggested experiments that were small, targeted, and ingenious. One proposal called for deliberate micro-excavations by rovers to trigger local changes in shading, texture, and thermal response, observing whether the rendering of the site altered with the manipulation. Another idea asked for transient electromagnetic stimulation of subsurface layers to see if their radar signature would transiently modulate, a sort of probing of state. More prosaically, it became clear that collecting a continuous vertical core through a seam and across a suspect pattern would provide the most decisive data, exposing whether repeating motifs were stratigraphic or simply surface textures. Meanwhile, beneath the pragmatic exchange of memos and proposals, there was a quieter motion, a current of private conviction among a small subset of scientists. This conviction was not evangelical. It was the shape of a suspicion that emerges from repeated anomalies coupled with no adequate alternative explanation. Those who held it spoke of echoes rather than certainties, patterns that felt like traces of a system once operating at scales of design beyond current comprehension. They imagined a civilization that had not been erased by tearing and burning, but had been paused, archived, compacted into more stable substrates. They entertained the idea that what remained might be less like a ruin than like a log file, readable by those with the right tools and questions. The emotional contour of that belief was complex. It mixed reverence, the sense that the planet might be holding a record of something enormously significant, with the clinical humility of scientists who know the cost of premature claims. The mood in the field alternated between a student-like thrill at the possibility of being the generation to decode a planetary record and a competence-fracturing awe at what such a record would imply about time and agency. There was also a social anxiety, the recognition that certain discoveries would not be purely scientific, that they would ripple into culture and philosophy with unpredictable force. Institutions that specialized in handling such data began to sketch ethical frameworks for release and interpretation, aware that the stakes were not merely academic. If the suspect seams were the footprint of archived complexity, what form could its remainder take? Materially, engineers imagined robust matrices, mineral lattices seeded with patterns at nano to macro scales, structures designed to survive chemical alteration and bombardment. Informationally, researchers considered redundancy, encoding the same pattern across mineral proxies so that simple loss would not erase the signal. Both strategies pointed toward an intention to preserve across deep time, a long view of legacy that humans themselves now explored when they built seed vaults and data repositories. The idea that another mind might have thought similarly, planting echoes across a planetary substrate, both comforted and unnerved those who contemplated. Yet the community remained careful. Extraordinary claims needed extraordinary evidence, and the evidence had to survive the crucible of cross-validation. Alternative models were continually refined. Could geochemical gradients produce low-entropy signals? Could regular fracture networks result from a rare confluence of thermal histories and lithologies? Could impact gardening preferentially expose certain textures that mimic procedural seams? Each challenge forced new measurements, deeper models, and, occasionally, the quiet recalibration of expectations. At its heart, the inquiry was not merely about proving the existence of an archive or a simulation residue. It was about learning to listen to a planet that had been shaped by time on scales that render human lifetimes as brief flickers. The telemetry anomalies, the too perfect planes, the repeating cracks, the seams that betrayed an unlikely regularity, functioned as a test of human patience and imagination. They demanded that observers refine their instruments, expand their analytic vocabulary, and, perhaps most importantly, broaden the kinds of questions they asked. There was a moral dimension to that change. If some of the planet's features were engineered with preservation in mind, then the act of discovery would be an excavation not just of matter, but of intention. That prospect urged a posture of stewardship to handle data and artifacts with the humility due to a planetary archive, recognizing that reading a record is an act that reshapes both the reader and the read. The same humility applied to the computational metaphor. Treating the planet as a repository rather than a playground encouraged strategies aimed at non-destructive inquiry, at the slow interrogation that deep time seemed to demand. In certain late hours, when the orbital feeds hummed and the control rooms dimmed, the imagery returned to the screens like a recurring sonata. Those cracked seams, those deceptively regular planes, looked less like an accusation and more like an invitation. Whether they would resolve into the remnants of engineering, into the artifacts of rare geophysics, or into a phenomenon that required an entirely new category of explanation remained unclear. The more important certainty was that the universe had delivered a question that refused quick answers. The story of those telemetry anomalies therefore became emblematic of a broader posture toward the deep past, a refusal to assume that absence implies non-existence, a willingness to cross disciplinary boundaries to decode whispers in stone and radar, and a patient acknowledgement that the traces of complexity can take forms unlike anything that has walked the surface of human experience. Echoes of a civilization. If echoes they were, would not thunder across the ages. They would murmur, embedded in seams and repetitions, inviting a species with a short history to lean in and learn the grammar of archival worlds. The work of listening, in that sense, was both a technical endeavor and a moral practice, a careful, reverent translation of the faintest signatures into narrative. What would a planet's last ledger look like? Not a photograph of a marketplace or a ruined skyline, but a ledger of consumption and repair, a ledger that ends in silence. That image, small and precise, became the hinge on which a new hypothesis turned, that Mars once supported intelligent, technological life, whose disappearance could be read not in toppled columns, but in the statistical fossils of resource flows and the quiet symmetry of erased code. The resource collapse theory began, quietly, as a way to bring together two stubborn observations. First, the planet offered no smoking gun ruins, no street grids visible from orbit, no city blocks standing in relief against the plains. Second, it kept returning suggestions of order in places that geology should have randomized: low-entropy spectral bands, subsurface lattices detectable by radar, repeated fracture motifs across otherwise distinct lithologies. Taken together, those facts resisted simple narratives. The earthbound explanation, that time and wind had effaced any trace of architecture, fit some of the data but left others oddly orphaned. Something in the patterns read like the end of an accounting, not the debris of a battlefield. Resource collapse framed these clues as a plausible life cycle of planetary civilization, one that ended not with a dramatic conflagration, but with a gradual or systemic depletion of the ecological and energetic substrates necessary to sustain complex maintenance. The theory set itself as both a geophysical and socio-technical account. It proposed mechanisms by which a society's material footprints could be selectively preserved, compressed into unusual mineral matrices, or intentionally archived as the society's capacity to maintain active systems dwindled. At the scale of a planet, resources mean more than individual commodities: voluminous water, accessible volatiles, energy gradients large enough to run industry and transport, and materials concentrated enough to permit manufacturing and repair. Each of those is a node in a systemic network. The collapse theory emphasized how feedbacks among nodes could cascade into a global shutdown. For example, progressive loss of atmospheric pressure, driven by chemical scavenging, solar wind stripping, or deliberate venting, would reduce the availability of gaseous transport for heat and volatiles. Reduced atmospheric buffering would expose water reservoirs to sublimation. As accessible water vanished, energy costs for extraction would spike. Energy deficits would force the abandonment of maintenance regimes. Pumps stopped. The material traces of such a trajectory would be subtle. Whereas a catastrophic societal collapse might scatter artifacts and burn away organic residues, a resource depletion ending would leave behind structures that, in losing their energy streams, gradually ossified. Pumps and reactors, once hot with chemical gradients, would cool and mineralize. Pipelines would oxidize and be incorporated into mineral veins. Active machines would be annealed into rock-like matrices by mineral deposition. Where maintenance ceased, sedimentary and diagenetic processes would rework engineered forms into textures that, to a cursory lens, appeared geological. But information theory offered an additional, more revealing lens. Systems that had been designed to operate at scale and reliability tend to leave low entropy. Thus, the second arm of the resource collapse theory, the disappearance of active systems, could paradoxically preserve informational redundancy. A society that understood the permanence problem might have, as it faced terminal resource loss, chosen to fold its most important records into stable substrates. If so, the archive left on the planet would not be a library, but a distributed, engineered sediment, encoded redundancies embedded in mineral lattices, repeated motifs across disparate media, and large-scale modularity that hints at infrastructural topologies rather than decorative design. The scientific apparatus responded to the theory with both rigor and new kinds of curiosity. Instruments that had been configured to search for organic biomarkers or standing architecture were retasked to test for signatures of engineered redundancy. Instead of looking for pottery shards and foundations, analyses searched for repeated isotopic ratios that suggested industrial fractionation, for mineralogical anomalies that defied expected diffusion profiles, and for geometric regularities at scales that survive weathering. Radar echoes were sifted not only for voids but for phase-coherent returns that suggested periodic substructure. Spectral datasets were compressed and then deliberately recompressed to reveal anomalous artifacts of encoding, the kind of low cosmology. These are not actions of characters in a story, but movements in a collective mind. The scientific community broadly conceived, adjusted hypotheses, proposed targeted observations, and designed non-destructive interrogations of terrain. The changes were procedural and institutional, new cross-disciplinary workshops, experiment proposals that combined geochemistry with information theory, mission briefs that prioritized long baseline radar scans and high-resolution isotopic sequencing. The work was incremental and patient, the kind of slow architecture of inquiry that the hypothesis itself required. Two essential contrasts emerged in modeling how a collapse might play out and how its traces might differ. The first is the unraveling collapse, a phase of rapid failure where interdependent systems cascade within a few generations. Pumps fail, distribution blinks out, crops are abandoned, and industrial reactions stop. In that scenario, the material world would still be littered with artifacts, but the social knowledge of how to repair or restart systems would be lost. Physical forms would be left mid-process and more visible to future observers. The second contrast is the graceful hibernation, a managed shutdown designed to preserve the intellectual core while abandoning the metabolic burden of civilization. Here, the last custodians might have attempted to migrate their most valuable configurations into. Which of these scenarios fit the data mattered. The absence of obvious debris favored the hibernation model, especially when combined with the telemetry anomalies that had shadowed earlier missions, seams-like crack patterns, suggestive of chunked representations, low entropy bands and spectra, and subsurface regularities inconsistent with stochastic geology. If Mars's last generations had, in the face of dwindling energy supplies, converted volatile dependent systems into mineral-stable encodings, those encodings would not announce themselves as ruins. They would be subtle regularities stitched across the planet's fabric. One practical implication of this reframing was methodological. The planet's archive, if it existed, might be legible only through the right interrogative posture. Traditional excavation, the noisy, invasive scraping of layers, risked both missing encoded patterns and destroying fragile, information-bearing matrices. Instead, non-destructive and multimodal sensing became priorities. Ground-penetrating radar with coherent phase analysis, tomographic imaging that preserves microstructural coherence, high-precision isotope ratio mass spectrometry, and nanoscale mineralogical mapping were combined into interrogation suites that thought in redundancy as well as in resolution. Computation. Detecting algorithmic residue in minerals required new interpretive frameworks. Researchers began to build null models of geological randomness against which potential encodings could be tested. They simulated diagenetic processes and asked whether repeated motifs could be generated by diffusion-limited aggregation or by repeated impact gardening. Where models failed to reproduce observed regularity, the residual space became the plausible domain of engineered patterning. This logic did not lead to attributing agency, it instead allocated probability. The evidence favored natural processes in the majority of cases, but in some narrow pockets the weight shifted toward unlikely order. Beyond the narrow technicalities lay the larger cultural consequence. The resource collapse theory reframed the discovery of encoded planetary heritage not only as evidence of ancient intelligence, but as a parable for technological endurance. If a civilization had chosen, in extremis, to transcode its achievements into long-lived substrates, that choice bore a profound ethical message, an awareness of mortality, and a preference for legacy over survival in place. The implications for humanity were immediate and uncomfortable. If preservation required trade-offs, energy diverted from active life toward archival stability, then choices about what to save, Where to place that saving, and who got to decide these priorities become moral as well as technical. There was also a cautionary reading. Resource collapse is not merely a distant, alien hazard. The dynamics that produce systemic failure, resource concentration, technological dependency, fragile infrastructures, were recognizable. The Martian example, if it was one, served as a deep time mirror for civilizations wrestling with similar tensions on shorter timeframes. The narrative that civilizations inevitably exhaust their niches is old. The nuance the hypothesis added was that exhaustion can lead to deliberate choices about legacy, choices that leave traces very different from the romantic image of a fallen metropolis. Philosophically, the theory sharpened questions about evidence and interpretation. An encoded archive would force the scientific community to confront how much epistemic humility is required when reading patterns across scales. What looked like redundancy could be natural repetition. What looked like preservation could be the stubborn persistence of particular minerals. Thus, the research agenda became twofold: expand detection sensitivity and expand the modes of skepticism. The goal was not to prove agency at every anomaly, but to refine the space in which agency could be assessed with confidence. Operationally, mission architecture adjusted. Where earlier probes had favored surface mobility and short-lived campaigns, planners wrote proposals for long-dwell platforms capable of repeated, phase-coherent radar passes and sustained geochemical sampling under controlled thermal cycles. Small, deployable arrays that sacrificed mobility for coherence precision were prioritized. Laboratory standards for handling returned samples tightened. If a mineral matrix carried encoded information at micro to nanoscales, contamination would be catastrophic to interpretation. Data curation, too, became a focus. The very act of selecting which datasets to preserve and how to compress them for transmission was recognized as an ethical act, one that could determine whether faint patterns. Emotionally, the hypothesis animated a complicated nervousness. There was wonder at the possibility of non-terrestrial decision-making about preservation and at the prospect of reading an alien ledger. There was sorrow at the thought that the civilization's legacy might be a record of choices made in exhaustion. There was a sharpened humility, the sense that the observable universe might store long, patient answers in forms that human senses and instruments were not yet trained to see. That humility translated into a methodological patience, an acceptance that the work of decoding could take generations and that the interpretive frameworks might need revision as new kinds of evidence accumulated. In the end, the resource collapse theory was conservative in its demands and ambitious in its consequences. It did not insist on a populated present nor on melodramatic ruins. Instead, it proposed a landscape of possibility in which intelligence once shaped planetary systems, and then, as the system's carrying capacity waned, chose to transmute the record of that shaping into forms resilient to time. The theory proposed experiments and instruments, it proposed a style of listening and an ethic of stewardship. And perhaps most poignantly, it posed a quiet question to any civilization that might one day read its traces: what will you choose to keep, and at what cost? Imagine a hard drive that was once full of lives, programs, and urgent logs. Its platter has long since been unspun, its active processes suspended, and yet, in the dim ambient hum of a data center with failed cooling, a faint LED continues to pulse. An errant heartbeat from an infrastructure with no operators left to notice? That image is the quiet kernel of a new, unsettling hypothesis. Mars as an emptied shell whose core, once harvested and transformed into labor and light, was finally exhausted. The users departed. The habitation moved on. But the system did not shut down cleanly. Small processes lingered. Background services kept ticking. Signal noise never stopped. This is not metaphor alone. In the data archives of missions across decades, investigators began to count anomalies that refused to fit tidy geological explanations. At first, the anomalies were almost comedic in their modesty. Faint carrier-like lines in radio spectra, narrowband spikes at frequencies that should have been empty, rhythmic microthermal fluctuations in regions devoid of solar input. They were the kind of detail that would sit, unremarked, in the margins of mission reports until pattern emerged from plurality. The noise persisted, recurring in places where no human or terrestrial spacecraft had left any active beacon. It was as if a shy machine had been left to its own devices and, for reasons inscrutable to present-day engineers, chosen to keep a very small light. To conceive of a civilization-dreadic core is to accept a scale that dwarfs human projects, able to thermal gradients, or to harvest the dynamo that nurtured a magnetic field would be a long, patient process. It would require techniques and thresholds that are, at best, speculative for contemporary engineering, but not for intelligent agents able to shape planetary interiors. In such a scenario, the habitable envelope of an ecosystem would contract slowly as accessible energy sources were flattened, as maintenance burdens rose, and as the cost of sustaining complex, active systems outstripped the means to do so. Chambers that had once spun turbines and chemostats would cool, active repairs would lapse, fabrics of control and life support would enter a state of graceful degradation. The occupants could choose to leave. Those routines are the kind of thing that leaves signature in the physics of a world. Every engineered system produces a trace, a regular thermal cadence from a pump that cycles at set intervals, a magnetic perturbation from a reaction whose current never quite reached equilibrium, a spectral line from processes that once refined isotopes for fuel. When the humans who now parse Martian data refer to noise, they do not mean random hiss. They mean structure whose statistical envelope is inconsistent with the messy, fractal unpredictability of natural processes. The signal is low, often submerged under the cosmic hiss of the interplanetary medium. But by folding years of observations, by cross-correlating sensors of different modalities, patterns began to cohere. From the vantage of a documentary-like investigation, the first task is classification. What is this noise? Is it an artifact of instrumentation, an interference from human satellites, or a genuine planetary phenomenon? That question shapes the modes of listening. The instruments themselves, radio telescopes, high-gain arrays, orbiting spectrometers, were repointed not toward spectacle but toward patience. Spectral analyses were run with windowing functions tailored to reveal long-period drifts. Phase-coherent stacking techniques were used to amplify whispers that repeat only over decadal baselines. The more patient the method, the more the noise maintained its shape. Narrowband peaks that should have broadened with dispersion stubbornly stayed needle-thin. Phase relationships among seemingly There is a particular poignancy in the idea of background processes outliving their users. In modern computing, daemons exist to enforce safety, to rotate logs, to check integrity, to reinitialize subsystems that drift. Left unguided, daemons can become ghosts, performing the same small task forever, consuming minuscule energy and generating patterns of resource use that are physically observable. On a planetary scale, a maintenance daemon might be a distributed network of pressure valves that still open and close under residual power, a thermal regulator that still modulates heat flow through engineered conduits, or a synchronization pulse that keeps a constellation of inert instruments aligned. These processes could be designed to be exceptionally fault-tolerant, built with redundancy precisely to survive epochs. The metaphor of Mars as an unwiped hard drive extends into how those whispers might be organized. Data retention strategies are never merely accidental. To be legible across deep time, records must be robust to noise, to random deletions, and to the slow chemical incursion of the environment. Error-correcting structures, repetition, parity schemes, checksums survive in the form of redundancy. If an archive were encoded into mineral fabrics, the same pattern might be distributed across multiple substrates so that the loss of any single layer still permits reconstruction. That distribution produces low-entropy regions when viewed naively, repeating motifs more compressible than natural noise. When Earth-based analysts ran compression tests on radar, the operational response to such findings is cautious, not theatrical. There is a responsibility embedded in discovery, the responsibility to avoid corrupting what one investigates. On one hand, an untouched planetary archive might be humanity's first access to another civilization's mind. On the other hand, the act of probing risks altering the archive irreversibly. Thus, the community developed a new suite of strategies, non-intrusive interrogation, phased imaging, and passive listening designed to preserve the integrity of persisting processes. Seismic arrays were deployed at distance before any drilling. Electromagnetic stimulation tests were run at amplitudes orders of magnitude below thresholds that might change mineral phases. The emotional reverberation of such a posture is complex and unnameable if one insists on singular feelings. The scientific community, if that phrase is permitted as a collective attribute, experienced a mix, awe at the possibility of a running archive, a kind of existential loneliness at discovering processes maintaining themselves without users, and a shiver of caution. The awe is easy to describe. There is a special kind of reverence that attaches when one perceives intentionality across deep time. The loneliness is the flip side, an acute awareness that intelligence may once have flourished and then deliberately left. The caution is practical and moral, a recognition that the impulse to wake a sleeping system is not a neutral act, but there are technical paradoxes embedded in the idea of a system still running without users. Machine time and human time diverge. Processes tuned to planetary timescales will run with duty cycles and rhythms entirely foreign to human attention. Where humans expect daily diurnal cycles or heartbeat frequencies, planetary maintenance can be paced in centuries. A watchdog timer set to pulse once every 10,000 years is meaningless to a living generation, but perfectly sensible to a civilization that aims to survive geological rearrangement. Consequently, the faint pulses that Earth-era instruments detected could be the shadows of schedules not aligned with present-day curiosity. Detecting them required stretching the temporal envelope of observation, a demand that in turn. Another paradox is the question of intent. A signal that repeats, compresses well, and correlates across sensors might be, at one extreme, the product of deliberate encoding. At the other extreme, similar properties can arise from mundane engineering choices, manufacturing constraints, material periodicities, or even emergent physical rhythms. Resolving the scale of intent requires, inevitably, a chain of inference. Investigators must build null models of natural processes so comprehensive that any statistically improbable residue stands out unambiguously. That is a tall order. Geology is a patient, generative art, capable of producing pattern with long enough time and the proper boundary conditions. Consequently, beyond methodology and caution lies a deeper, reflective question. What does it mean to find a system left running by its own architects? For a civilization to leave infrastructure humming on an unpeopled planet implies a set of choices about legacy. The choice might be practical, leave certain environmental regulators on to preserve habitability for a future return. It might be ethical, maintain life support long enough to allow for the return of those displaced. Or it might be archival, deliberately leave detectable pulses as markers, a kind of cosmic postcard saying, "We were here." Each of these readings carries different moral freight. If the pulses were meant as markers, then they could be invitations, an ancient entity hoping to communicate. If they were inadvertent, this raises a further dilemma. Even if one could read the pulses, even if one could decode the redundancy and reconstruct a fragment of the ledger, would humanity be entitled to intervene? The choice to boot a sleeping planet is not merely technical, it is cultural, political, and ethical. On Earth, societies debate whether to open ancient tombs, to disturb permafrost-preserved microbial communities, or to release archaic pathogens unearthed by mining. On an interplanetary scale, those debates magnify. To awaken a background process that acts as a planetary thermostat could have environmental consequences. To trigger archival systems might erase data used for future interpreted work. The prudent posture is a kind. There is an ironic kinship between the Martian phenomena and human attempts to preserve our own legacy. Seed banks, vaults with records, and projects to store cultural memory in ultra-stable media are expressions of the same problem at smaller scale: how to make information survive the erosion of environments and the entropy of time. Those human acts are not mere vanity. They are expressions of value, decisions about what to preserve and why. If Mars contains an ancient civilization that made similar choices, then its background processes are not only technical remainders but moral documents, a record of priorities selected under pressure. Reading them would be learning about priorities chosen under the hardest conditions imaginable, the slow withdrawal of energy, the gradual. The signal never turns off then, not because machinery is stubborn, but because legacy is. The quiet, persistent noise is a testament both to the fragility of users and to the stubborn endurance of artifacts. Listening, in the patient way that planetary science demands, is an act of humility. It recognizes that the universe keeps records in forms that are not always legible to an observer trained in a different time and different milieu. The system's little heartbeat is an invitation to learn new grammars of evidence, to fold information theory into geology, to learn to recognize redundancy where geologists might have seen random, and to treat the quiet persistence of processes as historically meaningful. Finally, there is the emotional residue left in the wake of such a discovery, a mixture of smallness and urgency. Smallness because a planet can host systems and memories far older and more sustained than any single species' attention span. Urgency because the act of listening, of preserving, and of deciding what to do with a running system without users requires choices now that will shape what future generations, human or otherwise, will be able to read. The signal is not a summons. It is a mirror. In the faint regularity of Martian noise, humanity sees a reflection of its own questions about legacy, what to keep, what to let go, and how to leave traces that respect both the living and the archive. Mars, emptied of its caretakers, keeps its light on. The world watches, and what if the planet kept some of its secrets purposefully dark until someone looked in a particular way? What if the act of looking, the sequence of measurements, the angles, the instruments, the temporal cadence, did not merely record what was already there but coax detail into being? That is the quiet, unnerving premise behind the phrase "render on observation," the possibility that parts of Mars only reveal higher fidelity when probed with a specific choreography of attention. It is an idea borrowed from the world of graphics and computing, where distant geometry and textures are simplified until a camera moves close enough to demand detail, and pushed into planetary scales, where observation itself might function as a kind of key. The concept lands between two established anxieties. On one hand, it appeals to intuition gained from years of remote sensing, resolution matters, and certain phenomena simply escape coarse instruments. On the other hand, it amplifies previously whispered worries about agency and contingency. If detail appears differently depending on who looks and how they look, then exploration is not merely a passive inventory, but an active negotiation with a system that responds. This possibility reframes many of the ambiguous anomalies that have accumulated in mission logs. Seams like crack arrays, repeated low-entropy spectral bands, and whispers of structured emissions into a question about conditional revelation rather than. There are, broadly, two families of mechanisms by which render on observation could operate. One family is geological and chemical, latent processes that require a triggering stimulus to manifest. The other is informational and systemic, representations that sit at different fidelity states until an interrogative protocol prompts a higher resolution rendering. The work of thoughtfulness and of science is to keep both families live in the analysis, to design tests that can distinguish a physically latent response from an observer-conditioned unfolding of encoded detail. Consider the natural mechanisms first. Planetary materials are not inert. Many sorb, release, or rearrange when their boundary conditions change. Some minerals exhibit behaviors that are strongly non-linear, photochemical transitions that occur only when ultraviolet flux crosses a threshold, salts that deliquesce in thin films under momentary humidity increases, clays that swell when disturbed and then consolidate in new microstructures. Deep subsurface fabrics can remain metastable for eons until the pressure wave from a focused probe, or the thermal gradient induced by a lander's activity, nudges them into a new equilibrium. Microbial theories extend this. If life ever existed and persisted in near-dormant niches, it might respond to the disturbances of SAMP. Those phenomena are mundane in the sense that they obey chemistry and physics. Yet their consequences can be dramatic for interpretation. A sample that looks sterile in one protocol can become biologically active under another. A radar mark that reads as a uniform subsurface layer at one incidence angle can resolve into discrete reflectors under slight changes in polarization. In these cases, the planet is not rendering a world as a computational metaphor suggests. It is exhibiting conditional physics. But the epistemic effect is similar. Detail arrives only after an appropriately tailored intervention. The second family of mechanisms leans into information theory. If some features of Mars are encoded, intentionally or as a byproduct of long-ago processes, then they might be stored at multiple levels of fidelity, much like a compressed file that expands only when given the right algorithm. In an engineering analogy, the planet's state could include coarse-grained representations for economy, along with latent high-resolution substrates that are energy or observation-dependent. In that case, a particular series of interactions, directed probing sequences, coherent phase measurements, synchronous multi-sensor campaigns, would unlock higher detail expressions of what had been statistically latent. This informational view is not mystical. It is a formal hypothesis with testable corollaries. If patterns are archived in low-fidelity modes, they will show telltale transition behaviors when prompted, abrupt gains in local information content under the same spatial footprint, phase-coherent modulations across modalities, or reproducible decomposition into repeated motifs only after specific stimuli. The mathematics of compressibility, redundancy, and algorithmic complexity gives tools to operationalize these tests. One may ask, does a radar return compress more efficiently after a targeted series of electromagnetic pulses? Does a spectral fingerprint acquire new, low-entropy peaks only after a thermal cycling of the same substrate? Designing experiments to probe render-on-observation hypotheses demands a different posture from traditional exploration. Where typical missions prioritize single-pass surveys or opportunistic sampling, an interrogatory approach privileges conditional experiments, controlled perturbations followed by tightly scheduled multimodal observations. These are not dramatic spectacles. They are patient, iterative choreographies engineered to see whether the planet's response space contains states that only exist under particular observational regimes. A basic experimental architecture looks like this. First, map an area with broad, non-invasive sensors to establish a baseline of behavior, reflectance spectra, radar coherence, thermal inertia, and magnetometry. Second, impose a low-energy perturbation designed not to destroy but to nudge, a thermal pulse, a controlled light flux, a minute electromagnetic sweep, or a precision mechanical abrasion. Third, observe the same area in tight temporal sequence across sensors, searching for changes in entropy, compressibility, and phase relationships. Fourth, repeat with graduated amplitude, duration, and modality, seeking reproducibility. Finally, if and only if patterns recur this protocol embodies a paradox of care. To learn whether the planet holds conditional detail, humanity must sometimes risk altering what it seeks to read. The ethical calculus is thorny. On Earth, archaeologists and conservationists wrestle with similar tensions. Excavation inevitably changes context. Planetary exploration amplifies the stakes by orders of magnitude and stretches timelines into deep time. Therefore, a key principle emerges. Observation should be minimally invasive until robust evidential thresholds are met. The default posture is reverence for the unperturbed archive. The permissive stance to more invasive steps should be guided by stringent probabilistic gains in information and by global. If render on observation phenomena were confirmed, the consequences would ripple beyond science. Philosophically, humanity would confront an observer-dependent texture of reality on a planetary scale. The act of attention would not be merely epistemic, but constitutive. Certain features would exist as distinguishable only when an appropriate attentional protocol is applied. That realization reframes questions about objectivity, presence, and the boundary between discovery and creation. It would not necessarily mean that observing creates matter ex nihilo. Rather, observation would be understood as traversing a landscape of possible states, some accessible only under specific constraints. The moral implications are also substantial. If a planet's details can be toggled by observation, the observer acquires. There is also a social dimension to consider. The publics that follow missions, the political structures that fund them, and the scientific cultures that interpret them would all need new literacies. Communicating conditional revelation is harder than reporting a simple, "we found X." It requires explaining uncertainty, process, and the staged nature of inquiry in ways that respect both curiosity and restraint. Institutions must create frameworks for transparent decision-making about interventions, balancing the hunger for headlines with the long-haul ethics of planetary stewardship. Technically, render-on observation research drives novel instrument design. Sensors optimized for static survey must be paired with actuators capable of subtle, reversible stimuli. Imaging suites need phase-coherent radar systems that can stack returns to reveal transient coherence changes. Spectrometers should operate across dynamic ranges suited to both fleeting activations and long-term baselines. And algorithms become central, machine learning systems that can detect minute shifts in compressibility or identify reproducible low-entropy motifs across noisy datasets are essential. Crucially, those algorithms must be interpretable. Black box claims about discovery will not withstand the necessary scrutiny when consequences are as weighty. There are also mundane but practical challenges. Spacecraft operate within mass, power, and bandwidth limits. Long-term, repeated observation campaigns are expensive. The patience required, monitoring over months, years, perhaps decades, conflicts with political and funding cycles attuned to shorter horizons. Overcoming these constraints will require rethinking mission architectures toward long-dwell platforms, international consortia that share infrastructure, and data curation strategies that preserve raw telemetry for future analytic methods yet to be invented. Interdisciplinary collaboration is another necessity. The mathematics of information theory, the subtlety of mineral physics, the patience of geomorphology, and the ethics of conservation must converge. This is not merely an expensive administrative suggestion, it is a methodological imperative. Teams must co-design experiments so that a perturbation meant to reveal hidden structure does not inadvertently erase more delicate signals, and so that any evidence for conditional detail is evaluated against a suite of plausible natural and instrumentally induced explanations. The deep emotional color of this work is unmistakable. There is an almost childlike exhilaration at the prospect that the cosmos still reserves contingencies for the curious, that detail might be coaxed into light through the right regimen of attention. There is also a sober dread of hubris, the recognition that a species with a short history of planetary care is being asked to make decisions that could alter another world's archive. Underlying both feelings is an abiding humility, a sense of smallness in the face of temporal depths that dwarf human projects. Render on observation asks observers to slow down, to accept that the universe may not yield its complexity to the first glance, and that some truths require patient. Finally, there is a lesson for the human imagination. The render on observation hypothesis reframes curiosity itself as a practice that must be learned, legislated, and moralized. Observation becomes less like plucking a fruit and more like tending a garden whose blooms open only under certain sequences of care. The work of exploration then becomes a stewardship problem. How to craft attention that is rigorous enough to uncover hidden heritage, restrained enough to preserve it, and humble enough to accept that not every mystery must be solved now. Whether Mars actually harbors regions that need to be coaxed into detail remains an open empirical question. What is not speculative is the shift the idea demands from a culture of single-shot discovery toward a culture of conditional interrogation, long-term patience, and interdisciplinary humility. Render on observation, as an operational hypothesis, transforms anomalies into a laboratory for method. It asks scientists to design experiments that recognize observation as an axis of change, to build instruments that are both gentle and precise, and to steward inquiry with the ethical seriousness commensurate with the ages. In that invitation lies, perhaps, the most human of impulses, the desire to learn not just what a distant world What if Mars was never intended to be the whole story, not a final scene, but an opening act, a carefully staged tutorial in a drama that unfolded across places rather than in one place? What if the traces that scientists call anomalies are not the remains of a culture stranded in one lonely basin, but fingerprints left behind by a civilization that treated planets as levels in a larger project, landing pads, staging grounds, checkpoints on a route to something else? This is the unsettling, quietly hopeful proposition that opens the seventh part of the inquiry. Mars was just one level. The metaphor is simple and strangely fruitful. In modern computation, in worlds built for play or for simulation, complex systems do not render everything at full fidelity at once. They economize. They allocate resources by priority, close to camera, high detail, far away coarse approximations. Environments are instanced, background processes are throttled. When a player crosses a threshold, the engine streams higher resolution assets. When no one visits, textures remain low, shadows uncomputed. Scaling this idea up to planetary dimensions yields a way to think about disappearance and persistence that is neither supernatural nor nihilistic. It suggests an economy of attention and energy on a cosmic scale. If a civilization achieved the ability to move beyond its natal planet, the decision would be pragmatic as much as philosophical. Planets are heavy places. They hold mass and complexity in inconvenient ways. Gravity wells demand energy, atmospheres leak, weather tears at structures, geological processes recycle materials. The first settled or engineered world, the place where culture learned to build, to repair, to think about large systems, might be an efficient laboratory for invention. It is where long, hands-on engineering can be practiced at the scale of continents. Yet once a set of techniques, materials, and protocols is refined, the calculus shifts. Habitats that float in Lagrange points, ringed habitats. Thinking of Mars as a level reframes a set of previously puzzling observations. Anomalous seams, low-entropy spectral bands, and repeating subsurface motifs suddenly fit into a narrative where a planet is used as an initial workspace, a place to stage energy harvesting, to test resilience of materials, to seed off-world systems with calibrated outputs. The apparent absence of large, decayed cities becomes less paradoxical if those cities were never meant to last forever on the surface. Rather than being sites of permanent occupation, they might have been sites of permanent occupation, portable, repurposable systems designed to be dismantled, compressed, or transmuted for transport. The ruin, in this view, is not a failure so much as a transition. There are several plausible strategies by which an advanced civilization might have leveled up from a planetary home. One is the straightforward exodus. Societies invest in propulsion and migrate physically. Habitats, ships, and biospheres lifted into orbit, then reassembled in more energy-efficient locales. Another is substrate migration. Culture and intellect move into computational or nanotechnological media that no longer require a planetary surface as a base. This migration could be local, orbital arrays and intersystem habitats, regional asteroid belt networks, or interstellar seeded colonies, probes, slower-than-light arc ships. A third strategy is hybrid. Species remain as a distributed presence, keeping maintenance nodes on key worlds. Each strategy leaves characteristic traces. Physical exodus may leave behind partially dismantled infrastructure, concentrated caches of machinery, and energy gradients collapsed into different mineralogical states. Substrate migration, on the other hand, may produce systematic encodings, redundancies spread across mineral proxies, isotopic anomalies from deliberate fractionation, rhythmic electromagnetic housekeeping. Hybrid systems might leave asynchronous signatures, bursts of activity at nodes that persist for centuries, while others slip into dormancy. The observational footprint of a civilization that moved on is therefore likely to be diffuse, conditional, and spread across different modalities of detection. This distributed footprint complicates the search by expanding the question from what remains on Mars to what patterns recur across the system. If Mars were only one level, then the key evidence might not be located solely in its basins. It might appear as cross-planetary breadcrumbs, matched low-entropy motifs on Phobos and Deimos, echoing isotopic signatures on certain asteroids, correlated phase, coherent emissions from Lagrange point objects, or synchronized thermal anomalies across widely separated bodies. In other words, the signature of a civilization that uses multiple levels could be not a big city visible from orbit, but a faint choreography etched into the distribution of energy and information across many small things. There is also the practical economy behind leaving a planet in a partial state of preservation or logged-out condition. Rendering detail costs power, maintaining infrastructure in hostile environments devours resources. An exit strategy that balances preservation with economy might look like this. Choose what to actively maintain: critical archives, emergency life support caches, or navigational beacons. Convert other artifacts into low-energy, high-durability forms, mineral-embedded records, encoded redundancy, and then orchestrate a staged withdrawal. The result would be a planet that is not an abandoned city so much as an organized archive, a landscape of intentional absences where certain features are obvious to a trained probe and others are deliberately obscured or compressed. This framing carries methodological consequences for human explorers. If Mars was one level in a larger system, then a search for ancient intelligence must widen its aperture from single-site excavation to system-level correlation. Instruments should be designed not merely for high-resolution local surveys, but for synchronous multi-body campaigns. Radar and spectral data sets require cross-referencing against orbital and small-body observations. Phase-coherent stacking of returns should be tried across different objects. Long-duration monitoring of Lagrange points and Trojan clusters could reveal the administrative scaffolding that once supported planetary networks. Algorithms for anomaly detection. There are also telltale signs that would favor a multi-level narrative over simple terrestrial erosion. Repetition at scale. The same geometric motif appearing on different lithologies and at different latitudes resists the randomizing influence of independent geologic histories. Coherent cross-modal emissions, matching narrow-band harmonics in radio and minute thermal cadence in the infrared, suggest a common clock or maintenance protocol, and patterns of material redistribution inconsistent with plausible geophysical processes. For instance, concentrations of high-grade ore in arrangements favoring extraction without obvious natural transport mechanisms could point toward an engineered supply chain repurposed in haste or design. Speculative as it is, the Mars as level hypothesis also reshapes the emotional architecture of discovery. There is a peculiar mixture of grief and exhilaration in the idea that a civilization once lived, worked, and then moved on. Grief, because the visible drama of ruins, toppled towers, empty marketplaces, may be absent, leaving only the trace logic of choices. Exhilaration, because a civilization that planned its exit or its translocation offers a different testament, not of collapse, but of foresight. The notion of moving on suggests agency that survived crisis long enough to make strategic, perhaps ethical, decisions about legacy and continuity. If the object of study is not a catastrophe, but a migration, then moral questions emerge that are not pure anthropological curiosity. What choices were made about what to preserve? Did the architects of the withdrawal favor genetic, cultural, or technological continuity? What ethical calculus led them to leave behind certain caches and to carry others? These questions matter because they shape what future discoverers, human or otherwise, might find: seeds of knowledge chosen under duress, fragments of thought reserved for distant readers. There is also the stubborn hope embedded in the idea. If Mars was simply the first level, then the civilization that learned there did not vanish into oblivion. It moved, perhaps, to orbital habitats that now drift unseen, to the asteroid belt where radiation is less punishing, or onward to worlds beyond the system. That possibility reframes absence as a clue to survival strategies rather than as an omen of failure. It invites humility and strategic patience. The cosmos may be populated not by visible ruins, but by quiet, mobile presences whose continuity is expressed in trajectories and system-level architecture rather than in monuments. Practically, this suggests a different kind of outreach for the scientific community. Collaborative, multinational arrays with the express purpose of system-level surveillance are needed. Telescopes and radars that track correlated anomalies across dozens of nodes, spectral libraries tuned to cross-compare mineralogical fingerprints across small bodies, and data archives designed to preserve raw telemetry for decades so that emergent pattern detection algorithms can be applied retrospectively. Simulations and null models must be constructed that encompass multi-body interactions, engineered material redistribution, and the spectral signatures of intentional fractionation. At the same time, ethical frameworks must be built into the decision-making process. If Mars is an archive left in a deliberate state, then any intervention risks corrupting what remains. Minimal, reversible probing must be the default stance. International governance frameworks and consensus mechanisms should be established before major interference. The choice to excavate or to stimulate a site, to run a high-energy experiment, or to attempt to wake dormant processes could have irreversible consequences for the preservation of information and for future understanding. Finally, the Mars as level idea reframes the human condition in one clear way. It asks humans to imagine not just surviving on a planet, but learning to think across levels. The species must adopt methods and institutions that are planetary in scale and time horizon. It must cultivate a patience to match geological rates and an ethical maturity that acknowledges the rights of future interpreters, human or otherwise, to find an uncorrupted record. The narrative ends not with a tidy verdict, but with a posture. If Mars was merely the first level, then the clues remain distributed and patient, waiting for an approach that is both technically savvy and morally attentive. The universe in this account preserves its complexity, not always in grand monuments, but in the choreography of withdrawal, in the redundancy of encoded echoes, and in the faint, system-wide patterns that only reveal themselves when attention is broadened from sight to network.